The story of the advent of nuclear fission is fascinating. Pictured are pioneers Lisa Meitner, Otto Frisch, Otto Hahn, Enrico Fermi, and J. Robert Oppenheimer. A history of their efforts should be on your reading list. We'll skip that story and get right into this history-changing process, the breaking apart of certain atomic nuclei with the release of enormous amounts of energy. Nuclear fission involves a delicate balance within the atomic nucleus between nuclear attraction and the electrical repulsion between protons. The nuclear strong force, the subject of a previous lesson, dominates in the nuclei of all elements found in nature. But in uranium, this dominance is tenuous. If the uranium nucleus is stretched into an elongated shape, the electrical forces may push it into an even more elongated shape. If the elongation passes a critical point, nuclear forces give way to electrical ones and the nucleus separates. This is nuclear fission. It is induced by the absorption of a neutron. We call that induced fission. When it occurs spontaneously without a triggering neutron, say in Earth's interior, we call it spontaneous fission. This is a typical reaction. We see that one neutron starts the fission of the uranium nucleus and that the fission products produce three other neutrons, the particles in gray. Since neutrons have no electric charge and are not repelled by atomic nuclei, they make good nuclear bullets. Neutrons can cause the fissioning of additional uranium atoms, releasing still more neutrons, cascading to an avalanche of still more neutrons. This sequence is called a chain reaction, a self-sustaining reaction in which the products of one reaction event stimulate further reaction events. A chain reaction is nicely achieved when one tipped domino causes the successive tipping of many dominoes. A typical fission reaction releases energy of about 200 million electron volts. By comparison, the explosion of a TNT molecule releases only 30 electron volts. The electron volt, EV, is a unit of energy common in nuclear processes. The amount of kinetic energy an electron acquires in accelerating through a potential difference of 1 volt. About 1.6 times 10 to the minus 19th joules. Not a big deal. But what is a big deal is this. The combined mass of the fission fragments and neutrons produced in fission is less than the mass of the original uranium nucleus plus the original neutron that triggered the fission. That's right, less mass. The tiny amount of missing mass is converted to energy in accord with Einstein's equation. E equals mc squared. A tiny amount of mass converts to an awesome amount of energy. This energy isn't primarily radiation, as is commonly thought. Most of the energy is in the form of kinetic energy of the fission fragments that fly apart from one another. Electrostatic repulsion. A smaller amount of energy is the kinetic energy of the ejected neutrons, and an even smaller amount of energy is that of gamma radiation. What makes this an enormously big deal is that it can be self-sustaining. Each new neutron ejected by each reaction can cause the fissioning of 2 or 3 other atomic nuclei, releasing more energy in a total of from 4 to 9 more neutrons. This repeats, and a whole chain reaction can proceed at an exponential rate. Why do chain reactions not occur in naturally occurring uranium ore deposits? They would if all uranium atoms fissioned so easily. Fission occurs mainly for the rare isotope U-235, which at the present time makes up only 0.7%, 1 part in 140 of the uranium and pure uranium metal. Most uranium is the isotope U-238, which doesn't undergo fission when absorbing neutrons. Naturally occurring uranium is too impure to undergo a chain reaction spontaneously. Actually, about 1.7 billion years ago, when the percentage of U-235 in uranium ore was greater than today, because of the more rapid decay of U-235, There was a natural chain reaction in an ore deposit in what is now Gabon, Africa. This leads us to speculate about other fission reaction in Earth's interior. We wonder, what would be the fate of a baseball-sized chunk of pure U-235? As soon as a stray neutron bumped into it, watch out, an enormous explosion would result. But if the chain reaction was started in a smaller chunk of pure U-235, no explosion would occur. This is because of geometry. Recall our lessons on scaling. Remember why there is more skin on small potatoes than on the same mass of big potatoes? The ratio of surface area to mass is larger in a small potato than in a larger one. Likewise, there is more surface area per mass for a small piece of uranium than for a large piece. In a small piece of U-235, so many free neutrons escape through the surface that the chain reaction dies out. In a bigger piece, a smaller fraction of the free neutrons escape before triggering another fission. So the chain reaction builds up, releasing enormous energy. For masses greater than a certain amount, called the critical mass, an explosion of enormous magnitude may occur. Consider a large quantity of U-235 divided into two pieces, each having a mass less than critical. The units are subcritical. Neutrons in either piece readily reach a surface and escape before a sizable chain reaction builds up. But if the pieces are suddenly driven together, the total surface area decreases, and if the combined mass is greater than critical, called supercritical, the chain reaction builds up explosively. This is what happened in the nuclear fission bomb that was dropped on Hiroshima in 1945. The difficulty in bomb making, fortunately, is separating enough U-235 from the more abundant U-238. Scientists and engineers took more than 2 years to extract enough U-235 from natural uranium to make the Hiroshima bomb. A chunk of U-235, probably a little larger than a softball, was used in that historic blast. To this day, uranium isotope separation remains a difficult process, although advanced centrifuges have made it less formidable than it was in World War II. Be glad that isolating U-235 is difficult. We wouldn't want nuclear bombs to be anywhere as numerous as AK-47s in the world. Nuclear bombs are one thing, nuclear reactors are another, although sad to say, many people have the same attitude toward both. Physics distinguishes between the two. In the next screencast, we'll look at the role of nuclear fission in energy-producing power plants. For now, I want to leave you with a question. Why is a chain reaction more likely in a big piece of uranium than in a small piece? Until next time, good energy.